Hey, differential equations. Okay, we did really basic systems of equations in the last lesson. Now we're going to get into a little bit more complicated differential equation or systems of differential equations. And we're going to use, we defined an operator when we were talking about Laplace transforms. And so we're going to use an operator notation in order to help us figure these out. Now, these problems can get really long, but you can at least solve these systems of equations, which you can't always say about systems of equations. So because these are long problems, I did decide to break this up into 2 days. So expect to see another video probably showing another example. Okay, so we're going to solve system by use of operators, and just to remind you that this is a system of linear equations that have constant coefficients. And so again, we're very isolated into what type of systems we can use to solve this, but this does solve. And it says by the use of operators, so let's talk for a moment about operator notation. Operator notation uses a capital D. So dx dt will be simplified to just dx. dy dt will be dy. And so if we start getting into second derivatives, second derivative with respect to t would just be d squared x. And if we did the second derivative of y with respect to t, then that would be d squared y. Okay, and so if we wanted to rewrite the differential equation, 2 dx dt plus 3x plus 5 dy dt minus y equals e to the t, we could write that as, well, 2 dx plus 3x plus 5 dy minus y equals et. And the nice thing about these operators is that they follow all the algebraic rules. And so anything that we did with algebra, we can do with these operators. So for example here, since in these terms they both have an x in common, if we factor out the x, we get 2d plus 3, and those are both in terms of x. And then over here in these two terms, they both have a y, and so we can factor out that y, and we get 5d minus 1 y equals e to the t. Okay, and so we're going to use this notation in order to be able to solve a system of linear equations. So let's do an example. This again is going to be a fairly straightforward example. As I said in the intro, these can get really long, and so for this one I'm going to give a fairly straightforward example, and probably for the video for next week I'll give an example of one that is really long. I know earlier in the semester, I joked about the problems can get really long. This is what I was referring to. As I said, this one's not going to be too bad. The next one's going to be fairly long. So my example for right now is dx dt equals a negative 9y, and dy dt equals a negative 4x. As I said, these don't look too bad. So let's go ahead and change this into our operator notation. So this would be dx equals a negative 9y, and then dy equals a negative 4x. Okay, so just like algebraic systems of equations, we pretty much have two ways to solve this. We can do this through substitution, or addition, elimination. Addition, elimination. So let's talk about this elimination method. And really, elimination method is what we're going to talk about today. So first thing, in order to do this addition elimination method, we're going to do this one here, is let's move everything over to one side. So we have a dx plus 9y equals 0. And we've got a dy. Actually, let's put our x's first, now that I'm thinking about it. Let's do 4x plus dy equals 0. Okay, so let's talk about, remember in our addition elimination method, we have to decide what we're going to eliminate first. Let's eliminate x first, just because. So in order to eliminate x, well, notice that this side has a dx and this side has a 4x. So in order for those things to be the same and for us to eliminate that, then this will have to be multiplied by 4 and this one will have to take a derivative of. And then one of them has to be negative. So let's do, I don't know, a negative 4 here. And let's do a derivative on this side. So again, we're kind of treating this like algebra. And so when we do this, now we've got a negative 4 dx minus 36y still equals 0. And on the other side, we've got a negative 4 derivative of x plus a derivative squared of y equals 0. Because we're taking the, Because we're taking the derivative of the derivative. And so therefore we'll get a second derivative. So if I now add those two together, then this term will now cancel out. And we've got a second derivative of y minus 36y equals 0. So remember that this actually is the same thing as second derivative with respect to t minus 36y equals 0. Well, we just finished doing that last unit. We said, what's my characteristic equation? My characteristic equation is going to be m squared minus 36 equals 0. Solving that out, I've got m equals plus or minus 6. So my complementary solution would be c1 e to the 6t plus c2 e to the negative 6t. Okay, that's nice. So now we've eliminated x. We've got x, or we eliminated x, we've got our y equation. So you now have to go back and figure out what the x is. And you can do that by taking this equation that we just found and plugging it back into one of the equations and then going from there. You definitely can do that. Or the way that a lot of textbooks do it is just say, okay, let's now eliminate y. Eliminate y. So again, let's remember my two equations are dx plus 9y equals 0 and 4x plus dy equals 0. So if I now wanted to eliminate y, well, this one has to have a derivative times it, and this one has to get multiplied by negative 9. So when we do that, we now have a second derivative of x plus 9 times the derivative of y equals 0. And the bottom equation becomes a negative 36x minus 9 dy equals 0. So again, this time your y cancels out, and you have left a second derivative of x minus 36x equals 0. Again, this is another one. This is really the second derivative of x in terms of t minus 36x equals 0. Well, our characteristic equation was m squared minus 36 equals 0. M's going to equal, again, plus or minus 6. So looks like our x equation in terms of t is also going to be, in this case, c3 e to the 6t plus c4 e to the negative 6t. But wait, 4 arbitrary constants? That doesn't make sense because we should only have, because some of that arbitrary constants were related to the other arbitrary constant. So now what we've got to do, because we're not done yet, now what we've got to do is take this and plug it into one of our equations. Well, take one of them and plug them into one of our equations. Let's take this. So if x is c3 e to the 6t, and c4, e to the negative 6t, that wasn't. And if I take the derivative of this, then I've got 6 c3 e to the 6t, and negative c64 e to the negative 6t. One of our differential equations says that dx equals a negative 9y. So we've got 6c3 e to the 6t minus 6c4 e to the negative 6t, and then minus 9, y we said was c1 e to the 6t plus c2 e to the negative 6t. Okay, well, in order for this to actually be equal, then we're going to have 6c3 equal to a negative 9 c1, or c3 is a negative 3/2 c1. And in order for the other two terms to be equal, we have a negative 6 c4 is the same as a negative 9 c2, or c4 is a positive 3/2 c2. So that means, coming to the very end, that our final solution is, let's see, y of t is c1 e to the 6t plus c2 e to the negative 6t, and x is going to be negative 3/2 c1 e to the 6t plus 3/2 c e to the negative 6, whoops, I forgot c2. c2 e to the negative 6t. And there's my answer. Okay, we will get a more complicated problem next week, and it will probably take 2 videos just for me to explain it. Again, if you guys have questions, please let me know.